Let's learn how to factor out a greatest common factor. When we factor out a greatest common factor, that means we break down a monomial or a polynomial down into its basic components and factor those out so that we have each prime component. So let's take a look at how we're going to do that. The first thing we're going to do is take a look at pairs of integers and make sure we understand how to break those down into their prime parts and make sure we understand how to get down to those basic components. So let's make sure that we can break these down and find those first before we move into variables and exponents. So let's take a look at 12 and 18. What we want to do is find the largest number that will divide evenly into those numbers so that we can break those down into its smallest component. Now if we look at 12 and 18, we might be able to readily see that 6 is the largest number that will divide evenly into 12 and 18. So the greatest common factor of 12 and 18 is 6. I'm just going to go ahead and tell you that. But if we didn't readily know that, what we could do is break these down into their prime factors and then find out how many prime factors they have in common. So that's just kind of a little trick that we can do. So let's just do a quick factor tree. I'm going to show you two ways to do it. I'm going to do it in the tree method, and then I'm going to do it just kind of lined out to see which way you like the best, and you can choose. So let's start with 12. If I'm going to do a factor tree for 12, what I'm going to do is I'm going to start with 12 and I'm going to just make a tree off here. And then I'm going to think of the first two numbers that come to mind, and you may think of two different numbers, and that's fine too. I think of 3 and 4. You might have thought of 2 and 6. It doesn't really matter. I think of 3 and 4, so I'm going to write 3 and 4 on my first tree. I look at 3 and 4 and I ask myself, are either of these numbers prime? In other words, can either of these numbers not be broken down any further? Well, 3 can't be broken down any further into two numbers other than 3 and 1. So there's no two numbers that'll divide into 3. So I'm going to circle 3, which means I stop on that branch. 4 can continue on, so I'm going to make another branch off of 4. 4 can become 2 times 2. Now I look at these two numbers and I ask myself, can these be broken down any further? Well, neither of those can be broken down, so I can stop with those. So now I want to break down 18. Well, I think of the first two numbers that come to mind, and those would be 2 and 9. Well, you might have thought of 6 and 3. That's okay. You would still do the same process. Well, 2 is where I'm going to stop on this side, and on 9 I'm going to go to 3 and 3. Well, I can stop with both of those because neither of them can be broken down further. So then what I do is I list out my numbers in a row. We want to list them in smallest to greatest so that you have them lined up the same. So 12, I'm going to list 2 times 2 times 3. These are the numbers I have circled. And for 18, I'm going to list 2 times 3 times 3. And then what I want to do is circle however many I have in common. I don't have another 2 with which I can make a match here, but I have a 3 that I can make a match with here. I don't have anything I can match this 3 up with, so I can't circle anything. So then I take and I multiply whatever I had to make matches with. So I had a 2 times a 3 to make a match, and that gives me 6, which I already knew in the beginning when I looked at 12 and 18 that 6 was my greatest common factor. So my greatest common factor of 12 and 18 was 6. Which I knew that, but if I didn't know, this is how I would have figured it out. So let's see how to do this with 10 and 35. So let's say I'm looking at 10 and 35 and I want to figure out the greatest common factor. Well, you may be able to look at that and already know that the greatest common factor of 10 and 35 is 5. So we can either do this tree method, or we can just go ahead and set up 10 and we can set up 35. And we can line them up out to the right here. So with 10, I'm going to ask myself, what two numbers might I multiply together to get 10? I'm going to multiply 2 times 5. And then I'm going to say, can I break up either of these? No, I can't, so I'm just going to stop. 35. Can I break up 35 into two numbers? Well, I can. I can break up 35 into 7 times 5. So I'm going to write 7 times 5, but I'm going to write it so that I write my 5 under the 5 that I have here because they match, and my 7 over here. I want to write them in order from lowest to biggest, and I want to match up whatever I can. I don't have anything to match up with my 2, but I can match up with my 5. Notice I'm kind of still doing the same thing of making matches. I don't have anything to match up with my 7. So the thing that I've circled is my greatest common factor. Had I had more than one thing to circle, I would have multiplied them together, just as I did over here. So my greatest common factor of 10 and 35 is 5. And there I've found 2 greatest common factors. So what do we do when we have variables? Well, really, it's kind of just the same thing. If we take our variables and line up what we have and circle the matches, then we can find our greatest common factor. So how many n's do we have when we have n cubed? Well, I have n times n times n. When I have n squared, I have n times n. And when I have just one n, I have n. So how many matches can I make? Well, I can make one match. So the greatest common factor for the n's is n. That's all there is to it. So let's look at this one. Let's line up each of our variables. I've got x squared, y to the 4th, x squared, y cubed, x squared, y squared. So I line up my x's with the first one. I have 2 x's and I have 4 y's. And then I have 2 x's and 3 y's. And then I have 2 x's and 2 y's. So then I need to circle wherever I can make a match. So I have a match here, and I have a match here. And then I have a match here, and I have a match here. But I can't make a match again for the y's, and I can't make a match in the last column for the y's. So I just stop there. So how many times did I make a match for the x's? Twice. So for my greatest common factor, I made a match twice for the x's. So that's x squared. And I made a match twice for the y's. So that's y squared. And that's my greatest common factor. Now, I want you to notice something. The smallest exponent that I had here for my x's was 2. And the smallest exponent that I had for my y's was 2. And look at my greatest common factor. They were both 2. So just keep that in mind. What happens when we find the greatest common factor for variables? We're looking for the most that they can all have in common. So when we're making those sets, if we see that pattern, all we have to do is remember that we're looking for the most number of variables that each of these monomials can share. So if this monomial has 2 x's, this one has 3, and this one has 6, there's no way that this monomial that has 2 x's can share more than 2 of these 6 x's. And this one couldn't share these 6 x's. So the only way for the greatest common factor to have x's in common is to have this minimal number of x's. So the greatest common factor is always going to just be your smallest exponent. Always. So, if you just look for the smallest exponent of each variable, then that's going to make your greatest common factor for that variable. So if I look through my term and I see that they all have an x, I'm going to write down x, and then I'm going to look for the smallest variable. So, or smallest exponent, I'm sorry. So the x squared is my smallest exponent. So 2 x's are all they have in common. So just to make sure you understand, Let me show you. I have 2 x's in the first one. I have 3 x's in the second one. And in the last one, I have 6 x's. So all I can do is share 2 x's. That's it. I couldn't share any more than that. And that will always be the case. I can only share the smallest number of x's that are there. So now the next variable I'm going to look for are y's. Do I have a y in each one? Yes, they all have a y. So y is going to be part of my greatest common factor. What are the most number of y's that they can all share? Can they all share 3 y's? This one doesn't have 3 y's it can share, and this one doesn't have 3 y's it can share. The most they could all share would be 1 y. So 1. And I don't need to write my 1. We don't usually write the 1. See, like here it's not written, but it's there. Z is my next variable. So Z has 5 z's, 9 z's, and 4 z's. The most they can all share is 4. So it's always just the smallest exponent that you see. So my greatest common factor is x to the second power, y to the first, z to the fourth. Let's try that on this last one. My greatest common factor is going to be all the variables that the monomials have in common and the smallest exponent that applies to those variables. So, do we have an x in common in all 3 terms? No, we don't have an x in all 3 terms, so x isn't even going to be a part of our greatest common factor. How about a y? They all 3 have a y, so we're going to include the y as our greatest common factor. The smallest exponent I see is a 1. Our z, I have the same exponents as I had in this example. So our z, they all have a z, and my smallest exponent is 4. And that's how we find our greatest common factor. Alright, so now once we have our greatest common factor, let's take a look at how to actually factor it out. So taking a look at this one, we have both integers and variables. So the greatest common factor in this problem, out of 3, 12, and 30, the largest number that will go into both 3, 12, and 30 is 3. And the largest variable that's going to factor out of n cubed, n squared, and n is just n, because that variable is shared by all 3 terms, and the smallest exponent is 1. So when we factor out a greatest common factor, we take that greatest common factor and we write it out to the side, because we want to know what it is we factored out. And then we open up our parentheses, and we're going to write what's left over after we take out that greatest common factor. And there's several ways to look at this, but how I like to look at it is essentially that I divided out this greatest common factor out of each term. And what's left over after I've divided out is what goes into these parentheses. And you should be able to just multiply it back through and come back out with what you started. So if I take 3n, and if I were to put it right here and divide this, let's see what's left over. So 3 goes into 3 one time. This n divides out one of these n's, and I'm left with n squared. If I divide this by 3n, 3 goes into 12 4 times, and I keep my signs. And this n divides out one of those n's, and I'm left with one of the n's. And then I divide this by my 3n, and 3 goes into 30 10 times, and this n just cancels that n out altogether. So I'm left with 10. And there's the factored form. Notice that if I were to multiply that back out, if I were to do the distributive property, I would get 3n cubed. 3 times 4 is 12, and n times n is n squared. 3 times 10 is 30n. And that's the same thing I started with. and that's what I want. So let's try another one. This one looks a little longer, but not difficult. I have 18, 12, and 24. So what's my greatest common factor of 18, 12, and 24? Well, the number that I think of for 18, 12, and 24 is going to be 6. That is the greatest common factor for 18, 12, and 24. I have an m and an n in both of those, or in all three of those monomials. So let's put an m and an n, and then let's figure out what exponents. So for the m, my smallest exponent, actually the only exponent, is a 2. For the n's, the most that all three can have in common is this 2. That is my smallest exponent. So now I just need to go through and divide that out of all three terms in the polynomial. So let's see what we're left over with. If I divide this out, and you don't have to keep writing this, eventually you'll get to the point where you can just see what's left. So we're left with 3, and this just cancels out. If I take 2 of these out of here, I'm going to have n squared. And then if I divide it out of here, this is going to cancel out, and I'm going to have 2, and 1 n is going to be left. And if I divide it out here, it's going to go in 4 times. And again, it's going to cancel out, and that is also going to cancel out. And I'm done. And you can realize whether or not you're done if you check out this remaining factor in here and make sure it's prime. Make sure it doesn't have any more common factors that can come out. If you still have factors that can come out, then that means your greatest common factor wasn't really your greatest common factor, and you missed a factor somewhere. So you can just factor again and take that factor out and multiply it times this factor out here. So that's a look at how to take out the greatest common factor when you see a polynomial that has common factors. Keep in mind you won't always have a greatest common factor, so don't freak out if you can't find a greatest common factor. If you don't have a common factor and you can't take one out, then take a look at one of the other factoring methods and see if that applies. If not, your polynomial may be prime. That is always an option.